Hi everyone, welcome to the second week's lecture on machine learning from eGATE.AI. I am Amrith, and this week we will look into linear regression and associated topics. So let's imagine a scenario where we would like to predict one variable using another. Or in other words, if I have to predict y using another variable x, I basically have to find a mapping between x and y, which is a function. So y is equal to f of x. Similarly, we can extend this notion to say that I can predict a variable y using a set of other variables, say x1, x2 up to xn. Now, where can this scenario apply in a real world scenario? So let's see, if I want to predict the YouTube views in the next week for a particular video based on a certain variables. Now what are those? It can be the video length, it can be the date it was posted, it can be the number of views it has received. Let's say x1 is equal to video length, x2 is equal to the date it was posted, and x3 the previous number of views it received. Similarly, I can think of another scenario where I am predicting which movies a Netflix user will rate highly based on their previous movie ratings, demographic data, etc. Now let's consider a more concrete scenario for which we have collected some data. So if you look at the advertising dataset, it is a dataset that consists of data for about 200 different areas, or we call it markets. So here an area or a market can be a city, it can be a state, it can be a country. It depends. So all we know is that yes, we have a data set where we have something like 200 different markets are available, and we know the budget that company spends for each market for marketing a particular product. Now we also know that the marketing budget is, or the advertising budget for each media separately, and we also know the sales they received in return. So what you see in this table here, it's a sample of 5 observations. So we mentioned that we have it for our 200. For the space constraints, we are assuming, or we are showing only 5 observations or data for 5 markets, and for each market I know, let's say it's market or observation, right? It's observation. For each market I know the advertising spent they have done on TV. So here the figure is in thousands of US dollars, so it's like 230,000 US dollar. It's 37.8 into 1000, or 37,800 US dollar. It's 69,200 US dollar, which has been spent in TV, radio and newspaper respectively for market 1, and in return they got a sales of 22,100 USD. For the time being, I'm not even sure whether the sales is the uh, amount in USD or is it some other metric, but it doesn't really matter as far as the modeling is concerned. So as far as I'm confident of the correctness of the data, all I know is that for a particular market, a company has spent a certain amount of money in advertising for TV, for radio and newspaper, and it has received a certain sales in return to the advertising spent. This is the information I can see here. So you can see that for market 1, you can see that for market 2, market 3, market 4, market 5, and there will be more up to 200 markets. This is the data we are going to deal with. So now if you see here, there is an asymmetry in many of these problems. So from the description of dataset itself, you might have already figured out that we have to predict the variable called as sales based on the spend the company does on different media for advertising. So we have to predict sales based on ad spending. This is the task we have to do. Now this might have occurred to you quite intuitively, but if you try to reason out why did that happen or why did we come to that conclusion, this is the asymmetry that we are talking about. So sales, this is the variable we would like to predict. It can be more difficult to measure, it may be more important than others, and it may be directly or indirectly influenced by the values of other variables. So these are some of the intuitive, let's say, rule of thumbs, or some of the it's basically the intuition that helps us determine what should be used for prediction and what should be predicted. So in this case, we are talking about two categories of variables. There are variables whose values we want to predict, and variables whose values we use to make our prediction. Now the values that we need to predict, they are often called as the outcome, response variable, dependent variable, or target variable. Similarly, the values that we use to make the predictions are called as predictors, features, or covariates. So it doesn't matter what term you use. It can be any of these terms. This comes because of the prevalence of the methodology in different domains. But it doesn't matter what terminology you use, but all of these terminologies are valid. So we may stick with, say, features and outcome, or features and target. But even when someone else defines it using terms like predictors or covariates, it basically means the same as features. Or when someone says response variable or dependent variable, it basically means an outcome. And now we have set the task, which was quite intuitive to us, but we have now formally set the task that it makes sense to predict sales. One, because yes, if we can predict like what is the sale we can expect given a particular budget we have, where budget is something where we have in control, it makes sense to see that whether we will get the return we want in a particular market, or whether a particular amount of budget is sufficient to make the uh, required sales. So here we predict the sales which is dependent on the advertising spend, where the advertising spend is again stratified into three different media: the TV, radio, and newspaper. So we are observing a number of variables and we are making sets of observations. So this is very important. So I have mentioned that we have data for about 200 markets, of which 5 are currently considered here. So we are making, this is a statistical modeling approach. It's a data driven approach. So data matters, and we can't do much with just one or even two data points. We need few of them. So we always assume that we have a set of observations. So in this case, we assume we have 200 observations or 200 markets. So each row is basically an observation, and we have n such observations, and we are making our prediction based out of this n observations or the 200 observations. Now each observation consists of a bunch of features, or we may say predictors. So every observation or each observation has p features. So we are looking at four different variables here, right? The TV variable, radio variable, newspaper variable, and sales variable, of which we are predicting the sales variable, and we are using TV, radio, and newspaper as our features or predictors. So naturally, in this case, we are having three features or predictors, and we are predicting p plus 1th variable, which is the fourth variable, sales, by using the other three variable. And we are making use of n such observations, where each observation contains p features and the target or the outcome variable, which is the p plus 1th variable. So this is the overall setup that we are talking about. So let's assume that the target variable y, so let's say the target variable y is related to the input variable x via f, which is expressed as y equal to f of x. Yeah, let's, for the timing, let's write just that. So here y is what we are trying to predict, in this case the sales, x is the observed values. So now the x can be a single variable or multiple variables. In the case of multiple variables, it can be represented as f of x1, x2 to xn. In our case, we only have three such values. So we also sometimes write it as f of x plus epsilon, where epsilon expresses an underlying rule of relating to the random amount that differs from the rule. Second thing is that even though we assume there is a mapping which is represented via the function f, so here we are assuming that the data in its original form, or the data originates based on a function f. So we are not trying to invent anything, we are not trying to create anything, we are basically saying that we are assuming that there is a functional relationship that exists between y and x. We are just trying to discover that function. This is the assumption. So by nature there is a mapping which is y equal to f of x, and we are trying to estimate that f, but unfortunately we don't know that f, so we have to learn it from the data. It's a data driven approach. The only issue is that since we don't know f, in reality we are trying to learn the y hat which is as close as possible to f. If f is the real the true function which is mapping which is providing the mapping between y and x, we are trying to learn f hat which is as close as possible to f, right, such that the predictions it make for new observations where we don't know the outcome, it is as close as possible to the true outcome. Otherwise, there is no point of predicting something if it is not resembling or reflecting the reality. So for the 200 data points that is promised here in this data set, in this advertising data set, we know the features or the predictors as well as the outcome. But for a 201st, so for an unseen input, what do you mean by unseen input? The target, okay, maybe let me rewrite this. So when the target is unknown, then I am basically trying to predict the best y or the best outcome which is as close as to the true outcome. So hence we say that, again, let me write it here. Y hat is what we are trying to predict. We are trying to predict it using a function called as f of x, such that the x is always observed. The input, the predictors, the features are always observable. So we use the same x. There is no approximation there. But f bar is close to f, where f is the, sorry, f hat is as close as to f, where this is the true function. Similarly, y hat is as close as possible to y for a certain x, where this is the true outcome, and this is predicted outcome. So we need something where this is as close as possible, or in other words, I can say y hat minus y should be equal to some, let's say, gamma, where gamma is less than or equal to 0.0001. This is desirable. I'm not saying this is always possible. I'm just saying it should be as close as possible.